All right, so let's talk about something called the common ion effect. So the common ion effect is when we are dissolving one of these slightly soluble salts, but instead of dissolving it in water, we're dissolving it in a solution that already contains one of those ions. So we're dissolving a salt in a solution that already contains one of that salt's ions. Okay, so let's look at what this really means. So here's again my generic example of a salt in equilibrium with its ions. And it would be like, instead of dissolving that salt into water, we're going to dissolve this solid salt into a solution that already contains one of the ions, one of the products. So remember what we know about equilibrium, what Le Chatelier's principle says, is that if we're dissolving this salt into a solution that already has one of the products, this would be like saying we're increasing the concentration of the products. That's going to shift the equilibrium back to the reactants. And remember what the reactants are. The reactants are a solid. So anytime you are dissolving a salt in a solution that already contains one of that salt's ions, this is always going to decrease solubility. So molar solubility in molarity or regular solubility in grams per liter is going to be less. Less of this salt will dissolve in a solution that already contains one of its ions. So let's see an application of this. So this question says, what is the molar solubility of silver 1 chloride in a 1 liter solution that contains 2.0 times 10 to the negative 2 moles of HCl, hydrochloric acid. The KSP of silver 1 chloride is 1.8 times 10 to the negative 10. So we're solving for molar solubility of silver 1 chloride. So we are going to use an equilibrium table like we normally would do when we're solving for molar solubility. The difference here is that we now have initially some of one of the products, this chloride ion. Remember, HCl is a strong acid, which means it's going to ionize completely into hydrogen ions and chloride ions. This is a 1-to-1 ratio, meaning if I have 2.0 times 10 to the negative 2 moles of HCl, I also have 2.0 times 10 to the negative 2 moles of chloride ions. This is in a 1 liter solution, moles per liter. That means this is the concentration of chloride that I start with initially. Because it's in a 1 liter container, this is the molarity. Remember, the only thing that goes in the equilibrium table is molarity. So I'm going to say we're starting with 2.0 times 10 to the negative 2 molar chlorine ion, chloride ion, when we start this. So we don't start with any silver ion. And now we're going to solve for X, because remember, X is the molar solubility in these equilibrium tables. The simplifying assumption is going to tell us that This x is negligible, so we're not going to need to do the quadratic formula because comparing the initial concentration to the KSP is going to show us that this x is negligible, and we can always double check that later too. So let's solve for x. So I'm going to say, using the KSP, 1.8 times 10 to the negative 10th equals x times 2.0 times 10 to the negative 2 plus x. Again, I can assume that this x is negligible, so it's really just x times 2.0 times 10 to the negative 2. So I'm going to divide both sides by 2.0 times 10 to the negative 2. And I'm going to get that x equals 9.0 times 10 to the negative 9. That is the amount of silver chloride that breaks apart. So the molar solubility equals 9.0 times 10 to the negative 9 molar. And we can see that x was negligible because 2.0 times 10 to the negative 2 plus 9.0 times 10 to the negative 9 is still going to be 2.0 times 10 to the negative 2. So this is the molar solubility of silver 1 chloride in a solution that already contains some chloride ion. So just to kind of illustrate this point, let's see what is the molar solubility of silver 1 chloride in water and compare that molar solubility to this molar solubility. AgCl, and we'll just say in water. The same KSP, so same thing, I'm going to say silver 1 chloride, silver 1 ions, chloride ions. This time, we do not have any chloride ions because we're just dissolving it in water. So now I have KSP 1.8 times 10 to the negative 10th equals x squared, x times x. I'm going to take the square root of both sides. X equals 1.3 times 10 to the negative 5th molar. So the molar solubility of silver 1 chloride in water is 1.3 times 10 to the negative 5th. The molar solubility of silver chloride in a solution that already contains chloride ions is 9.0 times 10 to the negative 9th. You'll see that the molar solubility decreases when you dissolve it in a solution that already contains one of the ions. So this is another good thing that you should be doing to make sure that your calculations are matching up with the chemistry. Anytime you are doing a common ion problem, the molar solubility should be decreasing. If you're getting a molar solubility that is higher than the regular molar solubility, you know you've messed up somewhere. So this is the common ion effect. It shows how a salt's molar solubility decreases when you are dissolving that salt in a solution that already contains one of its ions.